Okay. So today and tomorrow we will cover chapter 4, flow in pipes. Okay, and before this we have covered chapter 3, which is about apa chapter 3? Do you still remember or you not remember anymore? Apa? Tak dengar?
Equation. Semua tu.
Oh, okay, Bernoulli equation, yes. I think the finite volume analysis kan, chapter 3 that's very long chapter so for chapter 4 it's not long like chapter 3. I think we can finish it in 2 weeks, this week and next week. So now is week 10, so we have 10, 11, 12, 13, 14, so we have 5 more weeks. So chapter 4 will take 2 weeks, and chapter 5 we have the last chapter, chapter 5, which will take 1 or 2 weeks lah, and then we have few 1 or 2 weeks extra, and we can do more tutorial from the past year exam, and we can recap back lah chapter 3, 4 and 5. Okay, so in chapter 4, so there are few subchapters. Okay, 4 subchapters. Okay, the first one is the characteristics of laminar and turbulent flow in pipes and ducts, and the second one is losses in piping system. The third one is piping networks involving losses, and the last one is the application of the steady flow energy equation. Okay, so this chapter is quite related to the chapter 3, of course. It's relation lah, ada hubungan dia. In chapter 3 where you learn about the Bernoulli equation kan, as you mentioned before tadi, apa cakap tadi, and in that equation we assume that the flow has no friction kan, there's no friction losses, so that's why we just apply the Bernoulli equation, like can someone recall the equation again? Apa Bernoulli equation? Siapa ingat tak? Tak ada siapa ingat?
Yang P over rho G tu rasa.
Yang itulah. Apa? P, okay, betul dah. P1 over rho G, that's 1.
Plus Z1.
Yes, plus Z1. Plus
V1 over T.
V1 squared kan? V1 squared over 2G. And equal to P2 rho G plus Z2 and plus V2 squared over 2G. Okay, so we have this equation in chapter 3, and in chapter 4, in this chapter we will still using the equation, but now we take into consideration of the losses, because in chapter 3 we assume there's no losses, the fluid flows smoothly, and there's no anything, no friction, no heat, whatever. But in real life, as we discussed before, all flows have a friction lah, because of the interaction between the flow and the pipe and the wall, so there will always be a friction, and because of that you will have a losses. So that's why in chapter 4 we will understand how we can calculate that losses, and then we will include that in our Bernoulli equation, and this equation will be expanded. They will have more terms, including the losses in your pipe. Okay, so that is what chapter 4 is lah. Is a extension from chapter 3. Okay, so that's why you still also have a laminar and turbulent here, and we have discussed this in chapter 3 kan. We have already learn what is laminar flow and what is turbulent flow. So that's why in chapter 4 again we will discuss about that flow in order to find the losses in the piping system. Okay, so my plan today is just to cover this chapter 4.1 or maybe some of 4.2. Okay, and today we will do 4.2 fully and do the tutorial, do some of the question. Alright, So as an introduction, we all know liquid and gas flow through our pipes or ducts. Pipes normally yang ni lah, is circular geometry. So when we call pipes, that means the geometry of that conduit, that distribution network tu in circular geometry. And if you see ducts, that means that conduit and that pipe tu, not pipe, that network system tu is not circular in geometry. Maybe is rectangle ke or square ke. So that's is mean by that. Okay, so we use this a lot in our life, as for to flow in heating and cooling, and also in oil refinery. And if you go to any oil refinery, if I'm in Terengganu, we always see that in Kerteh, a big oil refinery there. Also if you go to Pengerang, there's another big oil refinery there. So you can see a lot of piping lah, to flow the oil and whatever lah. Okay, so that is in real life where we apply this fluid flow. So to flow the fluid inside the pipe or inside the duct, normally we will apply a fan or pump to flow that fluid. So there is a pump inside that piping network to flow the fluid lah. Okay, so that's why if you remember in Bernoulli equation chapter 3, we said that there's no mechanical device in that flow. The flow just move due to the pressure difference. But in real world, because we have that friction losses, so we need to supply additional power from the fan or pump just to flow the fluid. Okay, so that's why we have this pump lah or fan. Okay, so because of this flow has a friction, friction losses, so this will introduce, or this will result in pressure drop of the fluid. There will always pressure drop because of that friction, and heat loss. Okay, so ada pressure drop and heat loss, alright, during the flow through pipes and ducts. Okay, so this is the real world. So we now dealing with the real world problem lah. Okay, when you work in when you went outside, you finish your study and you work in, let's say, oil and gas or whatever, so you will dealing with this problem, and this is the theory of how we can deal with that problem. Okay, so because of we have that pressure drop, the fluid flow has a pressure drop, we need to put additional force, so that's why the pump comes in, and we need to know what is the pumping power requirement in order to give the additional drop, to cover back the drop, the pressure drop. So we need to have a pump, and we need to know what at what power, watt, how many watt we need to supply to cover back the loss. Okay, so this is what is in this chapter lah, chapter 4. So normally this is the circular pipe, we always commonly use in our real life, because circular pipe can withstand a larger pressure difference compared to a rectangular duct. Okay, this normally used in a lower application lah, where the pressure difference is not too big. Okay, because they cannot withstand a large pressure difference. Okay, so that's why we always see the industry use the circular pipe lah in the oil refinery or whatever. Okay, alright. So that's introduction. Okay, so because we are dealing with the fluid flow, okay, so we has to know whether the fluid is moving in a laminar or turbulent condition. So we have discussed this before in chapter 3. What is the difference between laminar and turbulent? Laminar is the flow in smooth manner, highly ordered manner. It's one layer, one by layer. So you can see a very smooth movement of that flow. But in turbulent, because of the velocity fluctuations, and you will see the flow has a very highly disordered motion, very have a turbulent zigzag and everything. Okay, because of the velocity fluctuation, you have this turbulent flow. And this we example in this chapter from the smoke. From the smoke, if you are the smoker, I hope you are not. Okay, I'm not encouraging you to smoke. Okay, just for example, if you see any smoker exhale the smoke from their mouth, you can see the first flow coming from the mouth is in very smooth flow, that's lamina. Okay, and after that you can see that smoke becomes turbulent, or what we call asap berkepul-kepul berkepul-kepul sorry. Okay, so that's where the turbulent region is. When the velocity becomes higher, then you will see that smoke in disordered manner, highly disordered manner. So that's where the turbulent region lah kat sini. The second one, after it comes from the mouth, it's very smooth, and then it becomes turbulent. Okay, so that's what how you can imagine lah, how you want to see lamina and turbulent. Just see any smoker exhale the smoke from their mouth, right? Okay, or we can do an experiment in the lab where we inject a dye inside this pipe. Okay, the dye, colored dye lah, any colored dye, so we can see the dye movement. So when inject the dye inside this pipe, okay, and then when the velocity comes, you can see this dye flow in very orderly manner lah, or we call as a lamina. The velocity not too high. Okay, but when the velocity becomes higher, as the velocities increase, you can see that the dye, okay, will move in very disordered manner, and this is where the turbulence flow is. So this is how you can differentiate between the lamina and turbulent. Right? Okay. So that is what is lamina and turbulent, as we have discussed before in chapter 3 as well. But there is one more, what we call as the transition. Okay, because lamina, to change from lamina to turbulent, it cannot change immediately. It cannot just from lamina to turbulent. It has one region in between where we call this as a transition. If you look from this example pun, there must be a transition region before the flow can change in fully turbulent. Okay, so this transition is region between lamina and fully turbulent. Okay, and we can calculate lah. Actually, we can calculate the number the what we call as Reynolds number, where this number will determine whether the fluid is in laminar condition or transition condition or fully turbulent condition. Okay, that's why we learn about Reynolds number. So this Reynolds number will determine whether the flow is laminar, transition or turbulent. So how we use this Reynolds number? Okay, to change from laminar to turbulent, normally the flow will depends on the geometry, the surface roughness, the flow velocity, and surface temperature, and the type of the fluid, whether it's oil or water or whatever. So this is the factors that will take into consideration when the fluid flow change from laminar to turbulent. As the velocity increase, so we can change that flow condition from laminar to turbulent. Okay, and so forth, so on so yang lain-lain itulah. But in 1880, okay, as thanks to Osborne Reynolds, So he introduced his discovery. Okay, he discovered that we can the main factors that will change whether from laminar to turbulent is the ratio between the initial force and the viscous force. So initial force the force initial lah, when the fluid flow. Okay, when the fluid flow will bring initial force, and there will be a viscous force yang akan lawan the flow. Okay, and the viscosity tu akan oppose that flow. Okay, so that ratio, the initial force and the viscous force, so this ratio will give you the number, and this number will determine whether the fluid is in a laminar transition or turbulent condition. Okay, so to find the Reynolds number, to calculate the Reynolds number, is just this equation lah. Okay, the velocity, the average velocity of the flow of the fluid. Okay, we know the fluid cannot have a constant velocity kan. At one point in the region tu dia akan ada profile of velocity kan. So that's why we use average velocity So the average velocity of the fluid flow times the diameter, D ni diameter lah, diameter of the pipe or of the duct. Okay, the diameter divide by the viscous force, kinematic viscosity, this nu, nu, and we know that nu is equal to mu, the dynamic viscosity, over rho n. So that's why from this equation we can translate this equation in terms of rho and dynamic viscosity as like this lah, because kinematic viscosity equal to mu over rho. So 1 over mu is equal to rho over mu. That's why you get this lah, rho times velocity average times the diameter over the dynamic viscosity. So this will give you the Reynolds number, and this Reynolds number is dimensionless. So there is no quantity. Okay, there is no meter ke meter per square ke, tak ada. It's dimensionless quantity. It's just a number. Okay, it's just a number to tell us whether the flow is a laminar, turbulent, or in transition. Alright. So far so good.
Yes.
Alright. Okay. So this is how he or Osborne Reynolds derive this equation. We don't need to know how he derived it. Okay. But if you curious, you can just Google and find how he comes up with this equation. But we as layman, we just use his discovery to calculate the Reynolds number. So this is the equation for Reynolds number. Okay, and S is a number, so the Reynolds number at which the flow becomes turbulent. Okay, there is what we call as critical Reynolds number. At this critical Reynolds number, where the flow is changing to turbulence, from laminar, and it starts to change to turbulent. Maybe it's not fully turbulent yet, but it starts to change into a turbulent region. So this for circular pipe. Okay, for circular pipe, the critical Reynolds number is 2,300. Okay, so when you calculate the Reynolds number, if you get 2,200, so that's still in laminar flow. So you know that flow is still in laminar, but when you calculate is more than that, 2,400. So that means the flow is already becomes turbulent. Maybe it's still in transition, okay, but it's not laminar anymore. Okay. So this critical Reynolds number is depends on the geometry. Okay, whether it's a circular or is square or rectangular. So that depends. But mostly because we are dealing in chapter 4, we are dealing with the flow in pipes. In pipe ni adalah circular pipe. So that's why this number is the crucial lah. When you calculate je, and you get the Reynolds number, you can refer to this critical Reynolds number, because mostly we are dealing with pipe. Okay. Alright. Okay, as the Reynolds number, I write again Reynolds number equation is equal to rho times V average times D the diameter over mu. Okay, so we have the diameter n. Okay, so Reynolds number always will depend based on this diameter lah, or what we call as the hydraulic diameter. Okay, so for flow through non-circular pipes, like this square, rectangular or channel, open channel, so the diameter of in the equation, we need to calculate that. Okay, and to calculate that hydraulic diameter, we call it as hydraulic diameter, is this equation. Okay, 4 times the area of the cross section, this area of the geometry, divide by P, which is the wetted perimeter. P is wetted perimeter, and we know perimeter ni lah, perimeter yang di yang mengelilingi geometri ni, and it's called, and it's wetted perimeter. Perimeter yang kena dengan air tu, yang kena dengan fluid tersebut. Okay, so we can calculate that hydraulic diameter using this equation. Okay, for example, for square duct, this is non-circular, for square duct, so we can calculate the hydraulic diameter using 4 times the area of this square duct is A times A, so that's why A squared over the perimeter, the wetted perimeter of this square duct, A plus A plus A plus A lah. So that's why you got 4A, and cancel out this, so it will give to you the diameter, the hydraulic diameter for this square duct will equal to A. Then you can use your equation here to find your Reynolds number flowing through this square duct. Okay, sama juga for rectangular duct. Okay, do it the same, find this hydraulic diameter from this equation, 4 times the area, so the area A times B. Okay, so that's why you got 4AB, divide by the wetted perimeter, A plus A, that's 2A, plus B plus B, so that's 2B. So that's why you have 2A plus 2B lah. And when you cancel out each other, you will get 2AB over A plus B. Okay, so this D you will use in the equation to find the Reynolds number flowing through rectangular duct. Okay, and similarly for channel, okay, you need to use the same equation, 4 times area, and we know it says here wetted end. Okay, apa yang air tu ada lah. Okay, that's why the area, the A times B, and of course they give you this height of that fluid. Okay, A times B, that like A, 4 times AB, divided by the perimeter, the wetted perimeter is A plus A and B, so 2A plus B lah. Okay, we don't take this B anymore because this open channel, and it's not rectangular duct or square duct, so that's why A plus B je. Okay, so you got 2A plus B. So this diameter, the hydraulic diameter, you can use in the Reynolds number equation to find the fluid flow, whether it's laminar or turbulent. So this is for non-circular pipes. But for circular pipes, okay, it's actually the same je. We'll use the same equation. But when you did the equation, it will comes back to the diameter of the pipe. If you do this, 4 times the A, pi r squared or pi d squared over 4, divide by the wetted perimeter, and to get the perimeter of a circular, you multiply pi with diameter, so pi d lah. So pi d is the perimeter of this circular. So when you divide this, eventually you will get only d. So the diameter of the hydraulic diameter for a circular pipe is just the diameter lah. Okay, so it's easy lah. If for a circular pipe, just the diameter of the pipe. Okay, so that's apa, whenever you see a problem, whenever they ask you to calculate the Reynolds number, make sure you know what is the geometry of that pipe. Okay, if they say pipe, so normally it's a circular lah. Okay, pipes ni always a circular pipe. Okay, but if they mention duct, then it's not a circular. Okay, it's not circular, and they will say lah whether it's a rectangular or square. Okay, they will always mention, always describe the conduit, whether it's a pipe or the duct. Alright, but mostly when you see any the past year paper or in a textbook, mostly we are dealing with pipe lah. Okay, that's why in chapter 4 the names of the chapter is flow in pipes kan. Okay, so normally we are dealing with the circular pipe lah, yang square duct macam ni jarang-jarang lah masuk, not very commonly asked. Okay, but we need to know this to find the Reynolds number through a different geometry of conduit. Alright, any question? Tak ada? Jelas?
Jelas, sir.
Alright. Okay. So Reynolds number, okay. Under most practical condition, and the flow in a circular pipes is laminar below 2300 and turbulent if the Reynolds number is higher than 4000, and between this number is what we call the transition flow. Okay? So this is crucial to remember. Okay, for circular pipes where we are mostly dealing, okay, any number below 2300 is laminar, and above 4000 is turbulent. This is what fully turbulent fully turbulent flow, and between this number this is where the transition flow. Okay, so as we see the experiment before from the diagram, when they inject the dye inside, as the velocity increase, you will see at first when the velocity tu kalau ada rendah, okay, you will get a very low Reynolds number, and you will get laminar flow. As the velocity increase, okay, you will see a transition flow first. Okay, that's why sometimes it's turbulent and sometimes they have laminar. Okay, so this region ni kat sini masih lagi transition lah, and after that there will be a fully turbulent flow. This means this here is more than 4000 lah. Okay, so that's how we can see this number in the experiment. Okay, alright, so that's Reynolds number, and that is subchapter 1 lah. So why we need to know to calculate this Reynolds number? Because we want to determine whether the flow of that the fluid flow in that pipe, so whether it is laminar or turbulent. It's important to note that, because when we want to find the losses in the piping system, it will depend whether the flow is laminar or turbulent. Okay, so that's why if you have looked up on the past year paper, the question for chapter 4 ni normally is combined together. Satu soalan tu 20 markah terus. And that's very crucial lah. If you cannot do that, that means you lost 20 marks. Because it's already they combine semua dalam satu soalan. Okay, so that's why step by step you need to know the Reynolds number, how to calculate that, and then you can use that information to calculate the losses, okay, in the pipe, and then you can calculate what is the pumping power that you need to add in your piping system. Okay, for this for today, so we ignore this part first because we not learn the topic yet. You can just answer the first question lah. the flow condition of water, okay, whether it's laminar or turbulent. So we go step by step lah, so that's easier for you. Okay, so examples 3, a water supply system for a building is shown in figure. So this is the figure, okay, your piping system network. So the flow rate of water being pumped, so ada pump, because we know we have a losses, so that's why we have a pump inside our piping system. So the flow rate of water being pumped is 10 liter per second. So what is this information? Ni apa? 10 liter per second ni? Anyone? Apa? Tak dengar.
Volume flow rate.
Yes, volume flow rate. So this is your Q lah. Okay, your Q equal to 10 liter per second. So because they give you in liter per second, you always need to change that in meter cube per second kan. So 1 liter is equal to 0.001 meter cube. Okay, so you will get 10 bagi darab 0.01 sama dengan 0.0001 0.01 meter cube per second. So that's your Q. And then they give you through 60 meter long. So this is your length of the pipe. So this is L. L will be equal to 60 meter. Okay. And 0.15 diameter. So your D is 0.15 meter. Galvanized iron pipe. So the pipe is made from galvanized iron. Okay. So we this is very important, but we look after this next class. Okay, why this is important? And they give you the money losses. So this also we will look at the next class. So the first question that you can answer today, they ask you to determine whether the flow is laminar or turbulent. Again, just use the Reynolds number equation. Reynolds number equal to rho times V average times D over mu. So you have your rho, the water is 1000. Okay, and you have the diameter 0.15, and you have the mu, the dynamic viscosity 1.31, but you don't have the V. How we can calculate the V? Anyone?
V tu kinematic viscosity.
Bukan? Ni V velocity bukan kinematic. Macam mana?
H velocity A1 V1 kot.
A1 V1, yes. From the continuity equation lah.
Yeah.
Q sama dengan A V kan. So you can find your V from continuity equation. Just divide Q, Q divide by A. Okay, so that's why they give you the Q. Okay, so you have the Q 0.01, and they give you the diameter, so you can find the A. So the A is equal to pi r square lah. Okay, pi times 0.075 square. Okay, so divide here, pi times 0.075 square. So you will get your velocity equal to 0.566, okay, meter per second. 0.566 meter per second. Okay, now you have everything. To calculate your Reynolds number, you just plug in everything. 1000 times 0.566 times the diameter 0.15, okay, divide by the mu, the dynamic viscosity 1.31 times 10 to the power of minus 3, and this should give you a value of 1000 1.566 is 0.15 divided by 1.31 minus 3. And you will get the value for Reynolds number is 64,809. So this value obviously it is bigger than 4,000, so you can conclude that this flow of water is in turbulent condition. Okay, as easy as that. Okay, boleh follow semua? Boleh? Ke tak boleh? Okay. Alright, so that's how you use a Reynolds number equation to calculate the Reynolds number lah. Okay, and the B, C, D ni kita tengok nanti lah. Tomorrow we will discuss about B, C and D. Okay, so again second example, they gave you here the water, again the row of water with 1000 with the dynamic viscosity 1 times 10 to minus 3 flows through a piping system shown in figure. The pipes are made of wrought iron. The length L and the diameter of each pipe are given as follows. So there are two different pipes. Satu pipe yang besar, yang ni. Another pipe, second pipe is pipe kecil, yang ni. So they give you the length of the pipe and the diameter of the pipe. So for pipe 1, the length is 60 meter, diameter 0.289, and pipe 2 yang kecil ni, because the diameter tu kecil, so that's why I call kecil. So pipe 2, the length is 22 meter and diameter is 0.194. Alright. So they give you the Q also in the question. Q is equal to 0.005. Okay. So you can calculate the first question. Yang ni biar dulu. Okay, ni we look tomorrow. Okay. So determine the Reynolds number and state the flow condition of water in each pipe. Okay. So you need to do two calculation lah. So pipe 1 and pipe 2. Okay. So you need to use the same formula. Reynolds number equal to rho times V times D over mu. Okay, and you have the rho, you have the D, you have the mu, and the mu. So you need to find the velocity. Okay, again as your tadi, to find velocity using the continuity equation. Okay, you can find the velocity for pipe 1. Okay, so V1 equal to 0.05, the Q, Q0.05, divide by the area 1 for pipe 1. Area for pipe 1 is pi times 0.289 divided by 2, 0.1445 square. Okay, so this will give you the velocity for pipe 1 is 0.1445 square, 0.76. Okay, 0.76 meter per second. And for velocity for pipe 2, the Q is the same. Okay, the Q ni sama je nanti equation kan. So the area is different, so you need to calculate the area. 0.194 bahagi 2, you will get 0.097 square. Okay, so this will give you the velocity for pipe 2, 0.05 divided by pi times 0.097 square. So this will give you 1.69 meter per second. Okay, and then when you get all this velocity, you can plug in the Reynolds number equation to calculate the Reynolds number. 1000 times V1 is 0.76 times D, diameter of the pipe 1, 0.289 divided by the mu 1 times 10 to the power minus 3. So this will give you 1000 times 0.76 times 0.289 divided by 1 times 10 minus 3. So you will get 21,900, no, 219,640. So this is much higher than 4,000, so it is turbulent. Okay, similarly do for pipe 2. Okay, the rho is 1000 times the velocity is 1.69, okay, times the diameter 0.194 divided by 1 times 10 power minus 3. So you also will get turbulent lah. Nombor lebih besar ni. 194 divided by 1 3. So you will get 327,860. So this is again much higher than 4,000, and this will be turbulent lah. Okay. Alright. So that's how you can determine whether your flow inside the pipe is laminar or turbulent, using the Reynolds number equation, rho times V times D over mu. Okay. Right. Any question?
Sir,
Yes.
Reynolds number ni dia tak ada unit lah.
Tak ada. It's dimensionless. So there is no unit for Reynolds number, as we mentioned here. It's a dimensionless quantity. If you look from the equation pun, okay, this V is meter per second, and D is meter, and kinematic viscosity is meter squared per second. Okay, and if you divide this, you will cancel out everything lah. S dengan S, meter squared ni mm, meter squared, this meter squared, so you cancel out everything. So it is dimensionless quantity. It's just a number that tells you whether the flow is laminar or turbulent. Okay.
Okay, sir.
Any more question? Okay. So that's it for part 1. So the thing that you need to remember is this. Okay, the number whether is below a laminar region or more than 4,000. But mostly, you will see the flow is turbulent lah. When we are dealing with a piping network, mostly the flow is in turbulent condition. Laminar ni very rare. Normally for very low velocity, and that's why in the real life in industry we cannot use a very low velocity of flow, and that's economical lah. So that's why we use a turbulent flow. Okay, that's why you will see when you do a problem, you will always, not always, sometimes ada juga lah laminar, but normally when you calculate, you will get the flow is in the turbulent flow. Okay, ada je lah yang laminar juga, macam contoh lain. Tak ada. Okay, tak ada. Okay, so that's it for today. Okay, I don't want to go into the next subchapter because you panjang lah nanti pening pula. So we still have our class next tomorrow. So we will discuss about these losses, and then we will do the question. Can we do that? Or you want to finish the class until 1:50?
It's okay. sir. My brain already full.
Okay. That's what I expected. Apa? So that's why I want to separate lah. So I think 2 hour session is not productive. Okay, I will split in 1 hour lah, or 1 hour each. Depends lah. Okay, so tomorrow we will see this subchapter losses in public system, and then we can finish the the question that we have already started kat sini kan. Mana yang ni? There are few more question kan, ada losses ni, so we can do this tomorrow lah. Okay, alright, so that's all for today. Thank you for your